Welcome to part 2 of our lesson on stereochemistry. In this part, we will focus on assigning R and S designations to chiral centers. This is an essential skill for understanding and describing the spatial configuration of molecules. We'll start with an overview of the RS designation system, explaining its significance and how it helps us distinguish between different enantiomers. Next, we'll go through a step-by-step process for assigning R and S configurations. This will include identifying the chiral center, prioritizing the groups attached to it, and determining the spatial arrangement. We'll then address challenges and examples to illustrate the application of these rules in various scenarios. This section will help solidify your understanding and provide practical insights into dealing with more complex molecules. Finally, we'll discuss mesocompounds, which are a special case in stereochemistry. Mesocompounds contain multiple chiral centers, but are achiral due to an internal plane of symmetry. By the end of this section, you will have a thorough understanding of how to assign R and S designations, and the ability to apply these concepts to a wide range of molecules. Let's get started with the overview on the next slide. The next step in our exploration of stereochemistry is to learn how to identify and assign the spatial configurations for chiral centers. Why is it important to specify the configurations at chiral centers? Recall that enantiomers are different compounds, so they must not have identical names. They have opposite configurations at their chiral centers, which we need to specify to accurately differentiate them. Chemists use the Kohn-Ingold-Prelog system to designate each chiral center as having either an R or S configuration. The letter R stands for right-handed, derived from the Latin word rectus, and the letter S stands for left-handed, from the Latin word sinister. This system provides a standardized method to describe the spatial arrangement of groups around a chiral center, based on the handedness of the chiral center. For example, consider the two molecules shown on the slide. The first molecule has the chlorine atom on a wedge bond, indicating it is coming out of the plane towards us. The second molecule has the chlorine atom on a dashed bond, indicating it is going into the plane away from us. These two molecules are enantiomers because they have opposite configurations at their chiral centers. If a compound has the R configuration at a chiral center, then its enantiomer will have the S configuration, and vice versa. This distinction is crucial for accurately describing and differentiating between enantiomers in chemical nomenclature and understanding their behavior in various chemical and biological contexts. Next, we'll explore the step-by-step process for determining the R or S configuration of a chiral center, starting with prioritizing the attached groups based on the Kohn-Ingold-Prelog rules. Now, let's go over the process for assigning an RS configuration to a chiral center. There are 4 steps involved. Don't worry, you don't need to understand all of these steps right now. You will learn how they work on the next slide when we apply these steps to various examples. Here are the steps. Step 1. Prioritize. Using atomic numbers, prioritize the 4 groups attached to the chiral center. Label these groups as 1, 2, 3, and 4, with 1 being the group with the highest atomic number, and 4 being the group with the lowest. Step 2. Look at the front. Rotate the molecule in space so that the group with the lowest priority, group 4, is positioned at the back, facing away from you. Step 3. Examine. Count the priorities of the groups 1, 2, 3, to determine whether the sequence progresses in a clockwise or counterclockwise direction. Step 4. Assign. If the sequence goes clockwise, the configuration is designated as R, right-handed. If it goes counterclockwise, the configuration is S, left-handed. It's important to note that a handheld model can be very helpful as a visual aid for this process, especially for step 2, where spatial orientation is key. Let's see how this process works on a real example on the next page. Let's begin the process of assigning an RS configuration with Step 1. In Step 1, our task is to assign priorities to each of the groups attached to the chiral center. Let's see how this works. To prioritize, we use the atomic numbers of the atoms directly attached to the chiral center. The atom with the highest atomic number is assigned the highest priority, which is 1, and the atom with the lowest atomic number is assigned the lowest priority, which is 4. In the example shown, we have a carbon atom bonded to a chlorine, a hydrogen, an oxygen in an ether group, and an ethyl group. Let's assign the priorities based on their atomic numbers. Chlorine has the highest atomic number among the groups, so it gets priority 1. Oxygen in the ether group has the next highest atomic number, so it gets priority 2. The carbon in the ethyl group has the next highest atomic number, so it gets priority 3. Hydrogen has the lowest atomic number, so it gets priority 4. With these priorities established, we are ready to move on to Step 2, where we will look at the molecule from a specific orientation to determine the R or S configuration based on these priorities. Now that we have prioritized the groups attached to the chiral center, let's move on to Step 2, looking at the front of the molecule. To do this, rotate the molecule in space so that the group with the lowest priority, which we previously determined to be hydrogen, faces away from you. Essentially, you should position the molecule such that you are looking at it from the front, with the lowest priority group pointing directly back. For instance, in our example molecule, the hydrogen, priority 4, needs to be oriented away from you. You can imagine turning the molecule so that the hydrogen atom is behind the chiral center, and you are viewing the remaining groups, chlorine, oxygen, and the ethyl group, from the front. This is the step where it is most helpful to have a handheld model, as visualizing the spatial arrangement can be challenging. We'll practice this step in the examples, and I will also show you an alternative technique to arrive at the correct orientation, usually without having to rotate the molecule. With the molecule properly oriented, we are ready to proceed to Step 3, where we will determine the order of the groups and assign the configuration based on whether the sequence is clockwise or counterclockwise. Let's continue to the next slide to apply these steps in a practical example. Now that we have the molecule oriented correctly, with the lowest priority group, group 4, facing away from us, let's move on to Steps 3 and 4, examining the order of the groups and assigning the R or S configuration. In Step 3, we count the group priorities, 1, 2, 3, to determine whether the order progresses in a clockwise or counterclockwise direction. If the sequence of priorities, 1 to 2 to 3, proceeds in a clockwise direction, the chiral center is assigned the R configuration. If the sequence progresses in a counterclockwise direction, the chiral center is assigned the S configuration. In our example, with the chlorine, priority 1, the oxygen in the ether group, priority 2, and the ethyl group, priority 3, let's trace the path from 1 to 2 to 3. If we trace this path and find that it goes in a clockwise direction, we assign the configuration as R. If it goes counterclockwise, we assign it as S. To summarize, a clockwise arrangement of priorities, 1, 2, 3, corresponds to R, right-handed. A counterclockwise arrangement of priorities, 1, 2, 3, corresponds to S, left-handed. This method allows us to systematically and accurately determine the absolute configuration of chiral centers in molecules, which is crucial for understanding their chemical behavior and interactions. On the next several slides, we will explore a few additional considerations that need to be taken into account when assigning R and S configurations. To help you understand these nuances and practice the method, we will work through several example problems. These exercises will not only reinforce the basic steps, but also extend our skills in addressing more complex scenarios involving chiral centers. There are several challenges we will encounter when assigning priorities to the groups surrounding a chiral center. One such challenge is prioritizing atoms of the same type. Consider the example shown on the slide. Note that the chiral center is attached to two carbon atoms. If these carbon atoms have the same mass, we need to use a tie-breaking method to determine which one has the higher priority. To break the tie, we look at the atoms directly attached to each of these carbon atoms. We compare these attached atoms based on their atomic numbers. If the atoms directly attached to the first set of carbons are identical, we move one more bond out and compare the next set of atoms, continuing this process until a difference is found. Let's use the example on the slide to demonstrate the tie-breaking process. First, notice that the chiral center is attached to two carbon atoms. Because these atoms have the same atomic mass, we have a tie. To assign priorities, we need to break this tie. I like to think of the tiebreaker as a type of runoff race, where the winner gets the higher priority. One easy way to keep track of everything is to draw a different shape around each of the tied atoms, for example, a circle and a triangle. This makes it easy to keep track of them. Next, in the space below the molecule, create a row for each of the tied atoms, placing the corresponding shape at the start of these rows. Now we need to see if the tie can be broken. For this, we look at one of the tied atoms, say the carbon with the circle, and identify the three atoms bonded to this carbon, moving outward from, not towards, the chiral center. So for this carbon, there is a bond to an oxygen atom, a bond to a hydrogen atom, and another bond to a hydrogen atom. Place these atoms, from highest mass to lowest mass, in the row for the circle carbon. Now go to the triangle carbon. This carbon is bonded to three carbon atoms, moving outward. So, list C, C, and C in the triangle carbon row. These two rows represent the races we will use to break the tie. We have three columns of races moving from left to right. In race 1, we compare an oxygen atom to a carbon atom. The winner is the atom with the higher atomic mass. If the two atoms have the same atomic mass, you move to the next race. In this case, oxygen has a higher atomic mass than carbon, so the tie is decided in the first race. As a result, the carbon with the circle is a higher priority than the carbon with the triangle. Now we can assign the R and S configuration to the chiral center in this molecule. We have oxygen with the highest priority, followed by the circle carbon, priority 2, then the triangle carbon, priority 3, and finally, hydrogen, priority 4. To complete the assignment process, we need to determine if the priorities are oriented clockwise or counterclockwise, from the perspective of the front of the chiral center. Notice that the lowest priority group, hydrogen, is not pointing away from us. It is pointing towards us. This means we are looking at the back side of the chiral center. We have two choices. One choice is to flip the molecule over 180 degrees, and then determine the orientation of our prioritized groups. Another option, and one I recommend, is to simply realize that because the molecule is backward, whatever we determine the configuration to be from this perspective, is the exact opposite of what it really is. So if we determine it looks like an R orientation, from the correct viewpoint, it would be S, and vice versa. Let's determine what we have. Our group priorities, moving from 1 to 2 to 3, show that from our perspective, the groups are oriented in a counterclockwise orientation. However, since the lowest priority group is towards us, instead of assigning S, we know it is actually R, because we are looking at the center from the back instead of the front. This tie-breaking method ensures that we correctly prioritize groups and accurately determine the stereochemical configuration of molecules, even when initial comparisons result in a tie. Understanding this concept is crucial for assigning RS configurations to complex molecules with similar substituents. Let's go to the next page and look at another detail related to assigning R and S configurations. Specifically, how we handle multiple bonds when assigning priorities. When prioritizing for the Kahn, Ingold, and Prelog system, We also need to know how to handle multiple bonds. For double bonds, we treat them as if the atoms are bonded to two single atoms. For example, a carbon-carbon double bond is considered as if each carbon is bonded to two single carbons. Similarly, for a carbon-oxygen double bond, the carbon is treated as if it is bonded to two oxygens. In the case of triple bonds, such as in an alkyne, we count them as three single bonds. This means that for a carbon-nitrogen triple bond, the carbon is considered bonded to three nitrogens. Let's look at the example on the slide. Here we have a carbon atom double bonded to an oxygen atom. For the purposes of prioritization, we treat this carbon as if it is bonded to two oxygens. Thus, the list for this carbon atom includes two oxygen atoms and one hydrogen atom. If we want to assign the configuration to the chiral center, we need to prioritize each group. Since the chiral center is attached to four carbon atoms, we face a tie-breaking task. I will diagram the entire process below. Notice that longer alkyl chains will have a higher priority than shorter chains, provided there are no bonds to heavier atoms or branching. Because the carbonyl group contains a double bond to oxygen, the carbonyl carbon has the highest priority, priority 1. This is followed by the butyl group, priority 2, the ethyl group, priority 3, and the methyl group, priority 4. The orientation of these groups from our perspective is clockwise. However, because the lowest priority group, the methyl group, is oriented towards us, we must reverse the result. Since we observed a clockwise rotation, which would normally indicate an R configuration, reversing this due to the orientation of the hydrogen gives us an S configuration. So, the chiral center in the given example has an S configuration. To make sure you feel confident with this process, your next step, after this lesson, should be to practice this skill in the homework assignment for the lesson. Don't forget to use your model kit to help, and as always, feel free to ask for help when you need it. Now that we have discussed assigning R and S stereochemical descriptors, we have one more item to cover in this part of the lesson: mesocompounds, which are discussed on the next slide. Now let's talk about a special category of compounds known as mesocompounds. A mesocompound is a molecule that has multiple chiral centers, but is achiral overall due to a plane of symmetry. This means that even though the molecule contains chiral centers, it is not optically active because it is superimposable on its mirror image. To illustrate this, let's look at the examples on the slide. The first molecule is a diol with two hydroxyl groups attached to a cyclohexane ring. Despite having two chiral centers, the molecule has a plane of symmetry running through the center of the ring. This symmetry means the molecule is superimposable on its mirror image, making it a mesocompound. The second example is a dibromocyclohexane. Here, again, there are two chiral centers. However, the molecule has a plane of symmetry that makes the two halves of the molecule mirror images of each other. The third example shows a diol with the hydroxyl groups on opposite sides of a linear carbon chain. This molecule also has a plane of symmetry, dividing it into two mirror image halves, thus making it a mesocompound as well. Mesocompounds are unique because they have fewer stereoisomers than predicted by the 2 to the power of n formula, where n is the number of chiral centers. This reduction in the number of stereoisomers is due to the internal symmetry of the molecule. Understanding mesocompounds is crucial for accurately predicting and analyzing the stereoisomeric possibilities of a given molecule. That brings us to the end of the second part of our lesson on stereoisomerism. In the final part of this lesson, we will delve into the optical properties of stereoisomers. We'll explore how these properties can be measured and quantified, providing us with crucial insights into the presence and behavior of stereoisomers in a sample. Join me in the next video as we continue our exploration of this fascinating topic.